Hello, my name is Junyoung Byun. Today I will present our research paper called On the Effectiveness of Small Input Noise for Defending Against Query-Based Black Box Attacks. Adversary attacks are divided into white box and black box attacks depending on whether the attacker knows about the internal information of the target model, such as weights and training dataset. Black box attacks are also largely divided into three types of attacks. Transfer-based attacks exploit the transferability of adversary examples and generate adversary examples from a local substitute model that mimics the target model. However, it assumes the attacker has access to the large training dataset to train a substitute model, and there is no guarantee for the success of the attack. Two other attacks are score-based attacks and decision-based attacks. They can check the target model's output through querying and gradually reduce the size of adversary perturbation. They are distinguished by the type of output they can get. In this paper, we focus on these query-based attacks and develop a simple but effective defense method against them. We target an implicit assumption of query-based black box attacks. That is, the target model's output exactly corresponds to the query input. We can defend against the query-based attacks by breaking this assumption with just a small input noise. We name this approach as small noise defense.
Compared to large input noise, small input noise almost maintains the clean accuracy.
However, this small input noise is surprisingly effective in defending models against the query-based black box attacks. This figure illustrates the working principle of SND against the decision-based attacks. Small input noise can effectively disturb the gradient estimation of decision-based attacks and score-based attacks. In our experiments on the ImageNet dataset, SND dramatically reduces the attack success rates of query-based attacks. Compared to other existing techniques, SND almost maintains the clean accuracy while it decreases the attack success rates even further. SND is also effective in defending against score-based attacks. Solid research for adversary defense requires evaluating the defense ability against adaptive attacks that exactly know the working principle of the defense. As an attempt to bypass SND, adversaries can average the noisy outputs via multiple queries for an input. However, the random noise is added to the input of the nonlinear function, and this makes it difficult to obtain an accurate output by averaging the noisy outputs. Using 10 queries for averaging the noisy outputs for each input did not significantly increase the attack success rates. Since many queries are required for getting a reliable output, these expectation-based attacks are not effective against SND. Interestingly, SND is very simple and easy for defenders, but difficult for attackers to bypass. SND is readily applicable to pre-trained models by adding only one line of code at the inference. In conclusion, we first highlight the effectiveness of small input noise to defend against query-based black box attacks. Our work suggests that query-based black box attacks should consider the randomness of the target network as well. Due to its simplicity and effectiveness, we hope that SND will be used as a baseline of defense against query-based black box attacks in the future. For more details, please refer to our paper. Thank you for your attention.